All right, let's go ahead and get started. A couple of things. Number one, today I'm covering the last little bit of the pumping problems of the more interesting style tanks and stuff. And then we're moving on to something called center of mass. However, because of the computer system and whatever like, your pre-section quiz for section 5.6, we put a special one on here called Centers, was actually due this morning like at 8 o'clock or something like that, which messed a lot of people up. So what I decided to do was I extended so if you haven't done your quiz 7.6 because you missed out on it because it was due supposedly today, but this 8 a.m. stuff, and usually I set my that's just before class at 11 o'clock, and I know a lot of you procrastinators out there just love to wait till the last minute to do this mess. I went ahead and just reopened it until Wednesday at 11 o'clock because I wouldn't discover this until after my last class and stuff. So I fixed all the due dates, so everything now is back to being due at 11 o'clock in the morning, so all your pre-section quizzes are due. But I've given you an extension on your 7.6 center of mass stuff. And again, just because the dates and actually the times had messed up because they all defaulted back to this 8 a.m. mess. And I always try to make it due just before class. The other thing, just to remind you guys that your homework number 5, test review number 3 is due on Friday by 2 p.m. You understand what you have to do? You've got to complete this thing and enter your answers on Canvas, just like before. Put your answers on the Canvas system. And you're going to turn in the free response part. Just the last couple of pages of this thing. Just the free response part. Stapled, last name first, first name last, put your section number on there, and you're going to turn it into Joseph, who's going to be basically getting all this stuff. And also, which means, this is all on Friday, which means that your test will be Monday, April 1st. So I got to get started working on a test for you guys. There you go. All right, let's pick up where we left off last time. And we just started this problem just to kind of give you guys a hint, because I really wanted you guys to kind of do this problem on your own. But let's see how well you guys can do on this thing. This, again, is a reality check kind of a problem. Now, if I'm going to bury a cylindrical shaped tank underneath the ground, I'm not going to put it upright. I'm going to lay the thing on its side so I don't have to dig so far in the ground. And that's what we got here. We got a tank in the shape of a cylinder on its side, has the following dimensions. It has a height on its side, which will be 15 meters, has a radius of 5 meters, and it's full of water. We want to find the work required to pump all the water out of a hole in the top of the tank. And I even put a little hole in the top of the tank for you right up there. We're going to pump it out to the top of the tank. Now, it's strictly up to you, but the first thing you have to do to any tank problem is you've got to put your coordinate axis on there. Because that coordinate axis sets up your integral, sets up your bounds, sets up the entire system. So, step 1, draw the picture again and look at the cross section of it. And because it's a cylinder on its side, the cross section is a circle, and you put your coordinate axis on there. And I told you guys, traditionally, I always put the coordinate axis at the bottom unless my cross section is a circle. To make my equations easier, I'm going to put the coordinate axis in the center of a circular cross section. And that's exactly what we got here. So I went ahead and put my x-axis and my y-axis on this thing, and I put it down the middle. So there's my origin 0, so the radius is 5, so this is 5 here, negative 5 on this side, and negative 5 down below. And my target is to get the water to the top of the tank. So we buried this tank like they typically do with when you go to the western part of the state up here behind a gas station. You don't see the tanks because they're underground, but the top of the tank is literally right at ground level. Okay? When you go to eastern part of the state where the water table is so high, you can't put things underneath the ground very much because your water table is like 3 feet down or something like that. So because of that, you typically see behind gas stations, you'll see the tanks actually listed up there so the tankers come by and pump it in behind the gas station or whatever. So this is what we got right here. So let's calculate the work. Formula you need to have memorized. Work is equal to the sum of the delta force times the distance that I have to pump. The delta force is equal to what I call water weight times your delta volume slice. So my delta force would be equal to, now what is water weight in this particular problem? Pure memorization. Pay attention to units. They're either going to be in feet or going to be in meters. This one happens to be in meters, which means it's the metric system problem, so your constant for water weight is 9,800 newtons per meter cubed. Your delta volume, I'm going to come over here and make a little delta Y slice. And when I make a little slice, you've got to imagine what this little picture is going to look like when you make this little slice. It's very, very thin, but it's either going to be a little disc shape or a little box shape. Because this is a tank on its side, so when I make that horizontal cut, in this example, it's going to be a little box shape. It is delta Y tall. The length has not changed at all. It is 15 meters, and it has a width of, you move away from the x-axis, the side of the tank is on a slant. So when you move away from the y-axis, you move in the x direction. This will be x. This will be x on this side. So what's my distance? Catch a pattern. It's 2x. So because this is a box, my delta volume equals length times width times height. That would be 2x times 15 times delta y, which makes it 30x delta y. That is my delta volume. 30x delta y. Okay? Now I'm going to clean my delta force up by just multiplying my constants. That 30 times 9,800 is, delta force is equal to 294,000 x delta y. So now to calculate the work, that'll be the sum of that delta force, which is 294,000 x delta y times the distance that you've got to pump. Again, you make these slices at an arbitrary y level and based upon your coordinate axis, and where in this case the top of the tank is based upon your coordinate axis, you calculate distance by top minus bottom. In this example, what is my distance? 5 minus y. The top of the tank, which is my target's at 5, minus the arbitrary y level, is going to be 5 minus y. Applying Riemann sum to integration, definition of integral, we come up with a formula for integrating this problem. Work would be equal to, constant goes out front, 294,000. Summation turns into integration of x times 5 minus y, and the delta y turns into the dy. And there is my equation for calculating work, but I got a problem. It's the same old problem. I got a big old x in the middle of my dy. So I need to come over here and find the equation for the edge of tank. The equation for the edge of the tank is your linking variable equation. This is a circular tank, and because I centered it at the origin, I'm going to use the famous x squared plus y squared equals r squared equation of a circle. However, what is the radius in this circle? It's 5. So I'm left with x squared plus y squared equals 5 squared. X squared plus y squared equals 25. Now the purpose of this equation, x squared plus y squared equals 25, is my linking variable equation. I want to go back in terms of my integration and replace x in terms of y. So I'm going to solve for x here. I'm going to subtract y squared from both sides. I get x squared is equal to 25 minus y squared, and I kill off a square by taking the square root of both sides. X is equal to the square root of 25 minus y squared. Because there's a big old minus in the middle, I can't break up my radical. It's not 5 minus y. It doesn't work like that. Only through strict multiplication division can you break up power or distribute powers or break up radicals. So that's pretty much it. However, I want you to understand what this x represents. And I know I'm not doing plus or minus because that positive square root actually is the equation for the right half of the circle, which is really what my x is representing. So work is equal to 294,000 times the integral of x, which is a square root of 25 minus y squared, times y minus 5 dy, and all I got to do is over my bounds. This tank was full of water. We want to pump all the water out of the tank. What are my bounds? Based upon my coordinate axis and where my water is, it's between -5 and 5. That is the answer. Now, here's the real deal. This is a nasty looking integral. You've done an integral like this before when we had our tables in the back of the book. Because what I would have to do would be distribute this square root, and you basically ends up being two integrals. One of them you can do with u substitution. However, the other one, you're going to have the tables of that a squared minus u squared form in the back of the book to be able to get it. So we're going to use this one. Clearly, it's going to be a calculator kind of a problem for us. So I'm going to, because I'm not going to give you tables on the test, I'm just going to say either, make my focus on this chapter is, again, setting up these integrals. And with the simple integrals, I'll make you integrate by hand. More complicated integrals, I'll tell you to use your calculator to integrate. I will let you do that. So 294,000 times the integral from -5 to 5 of the square root of 25 minus x squared over arrow, parentheses, times 5 minus x, close parentheses, dx. And then I hit integral, and it tells me my answer is huge. It's killing it. It's an awful integral. It's summing it up. It's sucking out my battery power as we're talking about it. And there's my answer. It is 57,726,765.13 watt. Don't forget your units. Joules. This is in the metric system. Does that make sense? Did I lose you guys anywhere? Questions? All right, before I move on to the next section, which is center of mass stuff, I want to do one more problem. So I'm going to pull out a problem that I'm just making up because I put this on a problem a couple of semesters ago and people died on it. It was embarrassing. So I want to see if you guys can sit and do this problem. Okay? And that problem is this. Let's say we have an inverted pyramid-shaped tank. You know what an inverted pyramid looks like. It looks like this. And it's a square base. Looks like this. And your tank, see if I can draw this thing, comes down here to a point. Okay? I'm going to set this thing up and let you guys practice with it. And on Wednesday's class, we'll actually do this particular problem. All right? So I want you guys to do it. So it's a pyramid-shaped tank. So it's square top, square base. And let's give ourselves some dimensions. Let's say this is 10 feet by 10 feet. Okay? And I'm going to tell you the height on this thing happens to be 12 feet. Full of water. Find the work done in pumping all the water to a distance of 3 feet above the tank. This will tell me if you guys actually have mastered this particular problem or not. So I'm going to give you a different kind of tank because this is what we like to do to you guys on the final exam. You've done hemispheres, you've done cylinders on their side, cones, you've done prisms, you've done troughs, you've done everything we can throw at you. Well, we're going to throw a different kind of tank at you. See if you guys can figure out this particular problem. We got a pyramid-shaped tank, inverted pyramid, that is. Okay? It's 10 foot by 10 foot square at the base, which is at the top. It is 12 feet high, and it's full of water. Finding work done, pumping all the water out of the tank. I just made this problem up off the top of my head. I want to see if you guys can do it. We'll do it on next class, but I want you to try it first. Try it. Don't just assume you know how to do it, because trust me, I put a problem like this on the test, and only a few people actually figured it out. Because remember, your coordinate axis is key. And by the way, what's your cross-section look on a pyramid, a inverted pyramid? What is it? It's a triangle. The side view, that's your cross-section look. Now, it's square at the top. That's great. But it's going to make, so it's square all the way down. And this is my last hint for you guys. It's going to be square all the way down. Just a hint. All right. Last little bit on this particular problem, though. And again, we'll do that problem next time. This particular problem, what if I gave you the $64 question, which I'm sure I'm going to put on your next test, pump half the water out of the tank. You don't have to do anything in terms of your setup and stuff, because it's going to be the exact same equation. The only thing that's going to change is your bounds. If I tell you to pump half the water out of this tank, what's your bounds? 0 to 5. Because when you remove water, you remove the top part, because gravity pulls the rest of the water down, and that's the water. You always integrate over the part you're going to remove. So if I remove half the water, that would, the bottom half would still stay there, and you would integrate from 0 to 5. That would have been my balance. The equation is otherwise identical. Does that make sense? All right, let's move on to the next section, which is section, still section 7.6, but we have made a special section on web work just for this called center of mass. Now, so I'm going to give you some terms. The center of mass, or centroid, means the same thing. Centroid's your fancy term for this stuff. Center of mass is typically what it is, okay? Now, I did some problems on the pre-section video, and because of the dates and times messing up on this pre-section video, I did make this section actually due next class period. I gave you an extension on this if you haven't done it yet. But hopefully, you took some examples and actually copied them down that I actually did on the video. Or actually, did you, the last ones that I did on the videos and stuff like that. And then we talk about the idea of what this thing's going to be, because we're going full circle on this one. So I did all these examples. So let's come over here to right here. Here are the formulas. Now, let me explain the whole idea behind center of mass. And the best way I can describe it to get people to understand. So, there are two different types of center of mass. You happen to have the center of mass, that is when your mass is a blob or a particular region. And the other center of mass you have is when you're actually hanging particular spots, putting masses at certain points on a coordinate axis. That's called the discrete case. When you have the discrete case, here is your formulas right here. When you have the continuous, or the region, blob-looking region there, that'll be the continuous case where you look at functions of tops and bottoms and the like. Now, the discrete case is very simple, because we've all done this thing. It's the concept of the mobile. When you did that in kindergarten or Sunday school or whatever, what you had was you got this little crossbar right here, okay? And at certain points on this crossbar, you hung little weights that your kids made. It's awesome, or you made as a little kid. And you hang it there. And then, of course, when your dad goes up there and tries to hang this thing, it's either going to flop one way or flop the other because of the weight. So he's got to put the string just right so it floats there in space perfectly. That point where the thing is, quote unquote, at equilibrium is called the center of mass of your system, okay? So, this is the discrete case here. And what you have here is some terms. You have something called the moment about the x, moment about the y, the total mass, and COM. COM is center of mass, or centroid. Now, the mass is basically the sum of the masses, okay, on your discrete case. On your continuous case, I'm going full circle on this, so I'm going to show you where these formulas come from. The mass is the density of whatever object you happen to be playing with times the area. Density times area gives you mass, okay? And so your density would be rho, and the area, when you have a continuous case, we're talking about a region where you actually have a particular top function f of x, you've got a bottom function g of x between a couple points of intersection a to b. So you're talking about a continuous region here, and you've got top and bottom. And basically it's area. And what is the formula for area? When you integrate, chapter 7.1, getting ready for your test, to integrate area, you integrate top minus bottom, f of x minus g of x, over your bounds from a to b. Okay? Now, in layman's terms, let me tell you what the moment about the x is. The moment about the x is the tendency to teeter or totter, or to rotate, if you will, around the x-axis. Okay? Now, to calculate the moment about the x when you have a discrete case. A discrete case is you have a particular coordinate axis and you're putting a particular mass at certain points. But to rotate around the x-axis, you've got to calculate the distance between the object where it's located at and the x-axis. And when you move away from the x-axis, moving away from my x-axis, you're using the y-coordinate. That is why the formula is the mass times the y-coordinate. And you take each mass, multiply times its y-coordinate, and you add it up. Okay? However, to predicate this concept in terms of the continuous case, the functions that define your region is in terms of x. And you are rotating it around the x-axis. Now, there is this volume concept to this, but it's not volume. We're trying to find the actual moment about the x, dealing with the density. The formula is the density, being a constant density that we're working with, divided by 2 times the integral from a to b of f of x squared minus g of x squared dx, top squared minus bottom squared dx. You would know this better as the functions in terms of x. I'm going to be rotating around the x-axis. I would use the disk washer. This is actually the disk washer formula, except instead of a pi to calculate that volume, we're putting the density concept into it. And pi is equivalent to the density divided by 2. So you get rho, your density, divided by 2 times the integral from a to b of f of x squared minus g of x squared. So remember that. The density is equivalent to, pi. Pi is equivalent to density divided by 2, or density is equivalent to 2 pi if you look at it the other way. Now look at the last one. The moment about the y-axis is the tendency to rotate around that y-axis, that teeter-tottering around the y-axis. But when you actually rotate and calculate volume around the y-axis, your function's in terms of x, and you're going around the y-axis. That's the shell method. The formula for shell method is 2 pi times integral from a to b of point radius times f of x top minus g of x bottom. When you go around the y-axis, your point radius is x. It is x times f of x top minus g of x bottom dx. But as I mentioned to you before, in terms of relating it to the density concept, your pi is equivalent to density divided by 2. So your density is equal to 2 pi. So instead of putting 2 pi out front, you put the rho density. Now, here's the good news. You should recognize these particular formulas as this is the shell method, disk washer method, and the area formula. You just have to put the density on them instead of pi's. So it's not a big stretch to memorize this stuff. The bad news is, in our problems, density is going to be constants. When we get you into Calculus 3, we're going to be talking about functional densities, because density doesn't always remain constant. Sometimes it changes. Like, for example, ocean water. Depending on how deep you are in the ocean, how dense the water is because of the weight of the other water on top of it. So the density changes. That's why you have things that go all the way, 4 miles down below the ocean level. You can actually still see some ships and some things actually preserving down there because the acidity level is not as bad, and things actually can preserve way deep down in these trenches and the Marianas Trenches and stuff like that. But if you're closer to the surface of the ocean, the density is a little bit lighter. You have a little more acidity into your water, the salt content, and then things tend to dissolve and basically rust away and melt away and stuff like that. So density changes is my point, just for your example. And that will be a function, so you'll have to put it behind the integral. And we got a whole new set of formulas called double integration integrals when we get you guys into Calculus 3. So you haven't seen the last of this stuff. All right, so this first example here is this. And again, the moment about the y-axis, since you're trying to rotate around or teeter-totter around the y-axis, you got to know that distance away from the y-axis, which is in the x direction. That's why you take the x-coordinate, multiply it times the mass, and sum it up. That gives you the moment about the y in the discrete case. So, here's an example for you guys. We're supposed to find the moment about the x, the moment about the y, and the center of mass of the system of objects with masses, and here's the point. We've got, at the point -2, 1, -2, +1. At this particular point right here, we've got the mass on object 1 is a 2, let's say it's a kilogram mass there. Okay, 2 kilograms I'm going to put there. At the point 1, -1, 1, -1 is right here. At this particular point, our little second mass is a 5 kilogram mass. And then at the third point, we got the point 4, 3, which is right here. At the point 4, 3, we've got a mass, little 3 here, which is a 3 kilogram mass. The object of the game here is to where can I put my point? Where is the center of mass? So if I can take the center of mass and put it at that point, I could actually hold this system in midair and it won't teeter-totter one way or the other. It will be, quote, unquote, at equilibrium. It will be at rest. It won't be flopping one way or the other. Does that make sense? Because everything would distribute out evenly throughout your system. So, first thing I want to do is you need to calculate the mass. The formula for mass is equal to the sum of the MIs. You add up all your masses. Well, no problem here. That would just be 2 kilograms plus 5 kilograms plus 3 kilograms. Don't hurt yourself. That's 10 kilograms, right? That's your mass. I added up all my masses. To calculate the moment about the x, it is the sum of the mass times the y coordinate. Because the moment about the x, because this bothers people, why is there an x there and a y there? To calculate the moment about the x, or the tendency to teeter-totter around the x-axis, is basically how far away is my mass from the x-axis. But when you measure the distance away from the x-axis, you're using the y-coordinate. Does that make sense? So what this would end up becoming is your first point, the mass is 2, its y-coordinate is 1, plus the second system, the mass was 5, its y-coordinate was -1, plus your third system, the mass was 3, and the y-coordinate was 3. So, trying to do this without a calculator here, let's see if we can actually do some basic math. That'll be 2 minus 5 plus 9, minus 5 plus 9 is 4, 4 plus 2 is 6. So the moment about the x-axis is 6. Does that make sense? Let's calculate the moment about the y-axis. The moment about the y-axis is the sum of the masses times the x-coordinate for the same reason. This is the tendency to rotate or teeter-totter around the y-axis, but I need to know the distance away from the y-axis, and the distance away from the y-axis is in the x direction. So this would be your mass. Your first system is 2 times the x-coordinate, which is -2, plus the second system, the mass is 5 times its x-coordinate, which is 1, plus the third system, the mass is 3 times its x-coordinate, which is 4. That gives you -4 plus 5 plus 12, and that is equal to 13. So to answer the questions, the mass is equal to 10, the moment about the x-axis is 6, the moment about the y-axis is 13, but now we want to have that COM, center of mass, also known as centroid. The formula for the center of mass is an ordered pair, it's a coordinate. The coordinates are your x-coordinate, known as x bar, is equal to the moment about the y divided by the mass, comma. The y-coordinate is the moment about the x divided by the mass. All right, so let's break this down. To actually calculate the x-coordinate, you use the moment about the y, because the moment about the y uses the x numbers, think about it, divided by the mass. And to get the y-coordinate, you use the moment about the x divided by the mass. So don't let the little subscripts throw you off. It depends on which variable which numbers you're actually plugging into it. So my x-coordinate here would be the moment about the y, which is 13, divided by the mass, which is 10, comma, The y-coordinate is going to be the moment about the x, which is 6 divided by 10. So if I write this down as a traditional ordered pair, this is 1.3 comma 0.6. So if I go over here to my system and calculate 1.3, here is 1, here's 2, 1.3 is about there. 0.6 is a little bit more than half, right about there. X marks the spot. This is my center of mass. So at that particular point right there, that is where I can hold the system, hold all these things being weighted down, and it would literally, quote unquote, float in space. It will not teeter-totter one direction or the other. This would be the point of equilibrium. This is where my center of mass is located at. Does that make sense? Questions? Got a question for you guys. Does your center of mass actually have to be within the system? Let's say I had a region that's the center of mass. Does your center of mass actually have to be in the region? Well, if I drew a region like this, it would be. If I drew a region that looked more like this, where would your center of mass be? Maybe right about there. Your center of mass does not actually have to be within inside the region that you're playing with. Does that make sense? Depends on what the region looks like, stuff. All right. So let's take a look at this problem here. Now the trick of this stuff clearly is going to be this, memorizing the formulas, because that's, well, this is Calculus 2, and that's typically what we do. So, this one I stole off of WebWork, and they like to use this fancy word, so here's the fancy words. Find the centroid lying between the regions of f of x equals the square root of x and g of x equals x squared. Centroid means find the center of mass. Well, first thing I'm going to do here is this. I'm going to draw my region. F of x equals the square root of x, no problem. Square root of x starts at the origin and bows out. This is f of x is equal to the square root of x. Graph. G of x equals x squared. I don't need a calculator for that one either. We all know what that looks like. That's a classic parabola. Comes here, gets the origin, and moves up. Here is your g of x equals x squared. Clearly, we're talking about this region right in here between 0 and the point of intersection. Where does x squared equal the square root of x at? Yeah, pretty much 1. 1 squared is 1, square root of 1 is 1. Yep, it's the point 1. Or the, so between 0 and 1. So easy picture for me to draw. I have my calculator in case it gets complicated, but this one's not. Now, when we ask you for a centroid, we're going to ask you basically 4 things. We're going to ask you to find the mass. We're going to ask you to find the moment about the x-axis, the moment about the y-axis, and then the actual centroid. That is the center of mass. Okay? So we ask you 3 things. Now, in this section, density, which is that rho, that little upside looking look like a little P thing called rho, it's a Greek letter. In this section, densities are going to be constant. We won't tell you the density, it's just going to be constant, so we just keep it as rho. On WebWork, because you have to enter in these answers, they're going to tell you what the density is. They're going to say the density is 5. Okay, so you use rho as 5, so you can actually type in a number, because you don't type in rho on WebWork. They'll tell you what the density is, so you just multiply it by it. So, this first problem, the formula is mass, which is by definition density times area. The symbol for density is rho. The formula for area, when I have a top and bottom, is going to be that f of x minus g of x dx from a to b. So this would be rho times integral from 0 to 1 of your top function, which is the square root of x, minus your bottom function, which is x squared dx. Does that make sense? So I'm going to come over here on this side and actually clean it up and integrate it. So your mass is going to be rho times integral from 0 to 1 of, I don't do square roots, it'll be x to the half minus x squared dx. This will be rho. Integral x to the half is going to be x to the 3 halves over 3 halves. Minus integral x squared is x cubed over 3, evaluated from 0 to 1. I'm going to clean it up. When you divide by 3/2, same thing as multiply by 2/3. This is rho times x to the, 2/3 times rho x to the 3/2. So it's rho times 2/3 x to the 3/2 minus 1/3 x cubed. Evaluated from 0 to 1. According to your fundamental theorem, and again, the rho's times all of this stuff. So this will be rho times 2/3 times 1 to the 3/2 minus 1/3 1 cubed minus rho times, pretty much when you plug in 0 on all this mess, you get 0. So 1 to any power is 1. So pretty much I got 2/3 minus 1/3, and 2/3 minus 1/3 is 1/3 rho. That's my mass. My mass is equal to 1/3 rho. And on web work, they're going to say, rho, the density of the object is 5. So you know what you would type into web work for this problem? 5/3. You just multiply, replace rho with 5 and multiply it so you can get a number to plug in, is what I'm saying. Okay? But on the test, I'm not going to tell you what the density is. I'm going to say the density is constant, rho, and you just have to write the answer 1/3 rho and leave it in rho as your answer. Now, what about the moment about the x-axis? The moment about the x-axis is the tendency to rotate around the x-axis, which, full circle, chapter 7.2, disk washer method. But remember, rho is equivalent to pi over, pi is equivalent to rho over 2. So, this, to rotate this thing about the x-axis here, I would use the disk washer method, but the disk washer is pi times integral of big functional radius squared minus little functional radius squared dx. You have that memorized. But pi is equivalent to rho over 2 times integral from a to b of your top function squared minus your bottom function squared dx. I'm just trying to relate how these formulas connect. So now, this would be rho over 2 times integral from 0 to 1 of your top function, which is the square root of x squared, minus your bottom function, x squared squared dx. So I'm going to come over here and actually integrate that. So this is the moment about the x, but when I clean it up, this gives me rho over 2 times integral from 0 to 1. The square root of x squared is just x. X squared squared is x to the 4th dx. So this will be rho over 2 times integral of x is x squared over 2 minus integral of x to the 4th is x to the 5th over 5, evaluated from 0 to 1. Fundamental theorem, plug in top minus plug in bottom. Rho over 2 times 1 squared over 2 minus 1 to the 5th over 5 minus rho over 2 times, plugging in 0 pretty much gives you 0 for all my terms. So let's see if you guys can do math without a calculator. This would be rho over 2 times, a squared is 1 divided by 2 is 1/2, minus 1 to the 5th is 1 divided by 5 is 1/5. What is 1/2 minus 1/5? Well, your common denominator is going to be 10. This will be 5/2 minus 5 tenths minus 2 tenths. 5 minus 2 is how much? 3 tenths. So your answer is going to be 3 rho over 20. Your moment about the x-axis is 3 rho over 20. And again, if on web work they tell you that the density is 5, you would type in 15/20 or 3/4, whatever you reduce your fraction, whatever it happens to be. Give them a number so that they want to give you that part. Now the last little bit is calculating the moment about the y-axis. The moment about the y-axis is a tendency for your region to teeter-totter around your y-axis with that constant density. The function is in terms of x, but we're rotating around the y-axis. That's the shell method, which is 2 pi times integral of the point radius times top minus bottom dx. Yeah. Would I switch them? Did I make double jog? Go check. The moment about the x is the tendency to rotate around the x. And, oh, wait a minute. Let's see, pi. Let's see here. Pi is equivalent to, let me go double check. My little formulas here. Hold on. The moment about the x-axis is rho over 2 times integral from A to B of top squared minus bottom squared. So you see what I'm saying?
Yeah, you just have the function on the next page.
Oh, no. Our next page is something different, sweetie. Wait, I'm gonna mess you up in a second. That's what I'm saying. These are the easy ones. Oh, hold on. No, these are the right formulas. But listen to me. This is how I know what they are. I'm actually not screwing this up here. I've done this before. Here's the deal. The moment to rotate around the x-axis is the disk washer method. Pi is equivalent to rho over 2. That's why it's this formula. The moment to rotate around the y-axis, your shell method. Shell method is 2 pi times integral of your point radius times top minus bottom dx. So, but because pi is equivalent to rho over 2, 2 pi is equivalent to rho times integral from A to B of your point radius, which is going to be x, times f of x minus g of x, top minus bottom dx. So this is rho times integral from 0 to 1 of x times your top function is the square root of x minus your bottom function, which is x squared dx. Okay? Wait, that second page is a different formula. So wait for just a second, because this is what they did to you guys. I got something in plan for you guys. Why I put it on there. But the next thing I want to do over here is clean this guy up. So this would be integral from 0 to 1. This is your moment about the y-axis. Integral from 0 to 1 of rho times x times, I don't do square roots. Square roots is a half a power. This is x to the 1/2 minus x squared dx. I'm going to distribute. And so this is rho times integral from 0 to 1 of, when I distribute, I add exponents, so it'll be x to the 3/2 minus x cubed dx. Now I'm going to integrate this guy, that'll be rho. Integral x to the 3/2, add 1, that'll be x to the 5/2 over 5/2, minus integral x cubed is x to the 4th over 4, evaluated from 0 to 1. Cleaning this up, this will be rho times 2/5 x to the 5/2 minus 1/4 x to the 4th, evaluated from 0 to 1. Plug in top minus plug in bottom, you end up getting rho times 2/5 times 1 to the 5/2 minus 1/4 times 1 to the 4th, minus plug in 0, you love that, pretty much gives you 0. And this pretty much gives me 2/5 minus 1/4. 2/5 would be what? And 1/4 common denominator is going to be 20 this time. So multiply by 4, that'll be 8/10 minus 5, so 8/20, excuse me. 8/20 multiplied by 4, and multiply by 5, that'll be 5/20. And 8 minus 5 is 3/20. So I end up getting 3/20 rho for this particular moment about the y. And so my moment about the y, when I type it up here, is going to end up being 3 rho over 20. Okay? Now, the formula for the center of mass doesn't change. It's a coordinate. It's a coordinate x bar comma y bar. To calculate the x bar, it's the moment about the y divided by the mass. To calculate the y bar, it's the moment about the x divided by the mass. The moment about the y is 3 rho over 20 here, divided by the mass, which is 1/3 rho. Got a question for you. What happens to my rhos? So this is 3 rho over 20 times, inverting it, that would be 3 over rho. What happens to my rhos? They cancel. And you're left with 9 over 20. Does that make sense? So this point is 9 over 20. Moment about the x. The moment about the x was 3 rho over 20, divided by your mass, which was 1/3 rho. So again, when you invert and multiply, that gives you 3 rho over 20 times 3 over rho. The rho's cancel. And 3 times 3 is 9 over 20. You get the point. 9 over 20 comma 9 over 20. This is your center of mass. And if you notice, you really shouldn't be surprised that the x-coordinate and the y-coordinate are the same, because look at your region. It's very symmetric. So here's 0 to 1, here's 0 to 1. So 9 over 20 is not quite half. So it's going to be, in this case, right there, right inside your region. Does that make sense? Now, what you were looking at before, because you're thinking I was messing up the formulas, is no, I've got the formulas down. But what they did to you guys on the final exam a couple of years ago was this. They asked a traditional find the center of mass problem. But instead of putting the functions in terms of x, they put the functions in terms of y. And people died on that problem, so we decided, what if the function is in terms of y? We decided ever since then, we'll just go ahead and talk about what the formula should be so you guys can catch the pattern on this thing. Okay? So, here we go. If the functions are in terms of y, this is a completely different set. The mass, if you notice that these formulas do not change because this is your coordinate pair and you're just plotting points. I didn't change these at all. What's going to change is this. Because instead of top minus bottom, when the functions are in terms of y, what do you happen to have? I got a function on the right. I got a right function and I got a function on the left, and the point of intersections are going to be from C to D, whatever those bounds happen to be. You got a right-left instead of a top-bottom. The functions are in terms of y. So you'll have an f of y here on the right and a g of y here on the left. So just to go through this stuff to make sure you understand, here's the concept. The moment about the y is the tendency to rotate around the y-axis. But if the function is in terms of y and you're rotating around the y-axis, what method do you use? Functions in terms of y going around the y-axis. It's the disk washer formula. But instead of top squared minus bottom squared, it's going to be right squared minus left squared. But it's the disk washer. So pi is equivalent to rho over 2 times integral from, I think I put c to d on these guys, c to d of your right function f of y squared minus your left function g of y squared dy. And if the function is in terms of y and you want to rotate around the x-axis, that's an opposite variable thing. This is the shell method. The shell method is going to be 2 pi times your point radius times your right minus left. Your point radius is going to be y. Your right is f of y minus left g of y from these points of intersection on the y, c to d, but your 2 pi is equivalent to rho. Your mass is still going to be kind of the same. It's density times area, but your area is going to be right minus left, g of y minus, f of y minus g of y. Ooh, there's my typo right there. The dy there and a dy there. Got to have y variables from C to D. But once again, your coordinates do not change. The moment about the x is the x coordinate is the moment about the y divided by the mass. Your y coordinate is the moment about the x divided by mass. Your formulas change when they change variables of your region. And the reason why we put this set of formulas on your exam, on the notes, is because it was about 2 years ago or something like that, 2 or 3 years ago, that they put a problem on the final exam, and they changed the functions instead of in terms of x, but in terms of y to find the center of mass. And everybody, okay, not everybody, 95% of the students had the coordinates literally backwards because they messed up the moment by the x, moment by the y, because the function was actually backwards on this thing. So that's why we put it on there. All right? We got a couple of web work problems on something like this, and I'll do a couple of these guys, but I'll finish them up next time. But this first one for web work is kind of an easy one. But this is one I give you guys because students screw this up. It doesn't get much easier than this from chapter 7.6. It says this. Find a particle. A particle is moved along the x-axis by a force that measures. Force is equal to 2x cubed plus 5 pounds. At a point x feet from the origin. X feet from the origin. X feet from origin. Find the work done in moving from the origin to 2 feet. And people look at this thing and don't know what to do. Formulas for work. Work is equal to force times distance when you don't have functions. Straight shot. And remember, work is all about lift. Work is also equal to the integral from a to b of f dx. That was one of our basic forms that we even used to set up all that stuff about springs. They gave you the spring function in terms of x, where x is your distance from the origin. So this would be equal to the integral of 2x cubed plus 5 dx from the origin is 0, to x equals 2 feet, 0 to 2. That's all you had to do is integrate this function from 0 to 2. Well, this is not difficult. Integral x cubed is x to the 4th over 4, so that'll be 2 over 4, which is x to the 4th divided by 2, plus integral of 5 is 5x, evaluated from 0 to 2. That'll be 2 to the 4th divided by 2, plus 5 times 2, minus plugging in 0, pretty much get 0. This is 10. 2 to the 4th is what? 16. 16 divided by 2 is 8. 8 plus 10 is 18 what? Pay attention units. Foot-pounds. This is the English system. Distance is measured in feet. Force is measured in pounds. 18 foot-pounds. We got one more to do, but I'll do that next time, and that is the famous triangle problem. But I want you to get used to these formulas first. I'll finish this up, and notice next time we're moving into Chapter 8.1, sequences. So study hard.